Hey guys, my name is Adrienne and welcome to Organic Chemistry 2, part 1 of these recorded sessions. So, today we'll be going over for most of y'all chapter 13 and in general mass and infrared spectroscopy. So, before we get started, this is the first video of OChem 2, and if you've watched the previous videos for OChem 1, this format is going to be a lot actually different because OChem 2 is a different beast, so we need to take a different approach. So OChem 2 is a lot of reactions, a lot of graphs, a lot of types of things like that. So I won't be able to draw all of it, obviously. So we're gonna be starting with review, review questions, official review questions from a test bank from your books. Um, so we'll do that. I'll have them up on the screen. You can screenshot them. You can fast forward or whatever, and then we'll do them together. So I'll have them up, pause, and then I explain. So that's how it's gonna go. And then afterwards, I'll have the key, and then after we're done with the review, we'll scrap it, and we'll go over must needs, right? We're not gonna go over every single detail in the chapter. Obviously, we're gonna be more focusing on um, the big topics, the high yield stuff. So unlike in OChem 1 videos, we did every single little thing and did practice questions as we went because they were more concept related and a lot of Gen Chem, so it is a lot of concept. But OChem 2 is just going to be reaction. So if you like reaction, great. If you don't, um, buckle up because it's going to get crazy if you don't like reactions. But other than that, you have all the tools you need. Your book has all the reactions, has all the breakdowns, so you shouldn't worry. Um, again, OChem 2, if you survived OChem 1, you can deal with OChem 2 because for the most part, it's easier because it is just reactions and it's just a lot of remembering and memorizing. But depending on your professor, again, um, they can be extremely detailed or very general. So ask them, make sure to ask them, or if you know anyone who's taken them, definitely check them out, check out the tests, what they're like, things like that. Or if you have an SI, definitely ask them, right? So again, this is for no specific professor or class, general overview, and pretty much you'll be hitting the important stuff, right? And once we do the review, all the little stuff will kind of just play out, and it won't be that big of a deal, and you'll see a lot of different variations of questions, and again, play with the questions, and yeah, these are good. These are good for you. Okay, so with that being said, let's get started with our first official review, right? Okay, so this is how it's gonna look like. You have questions here, so screenshot, pause, write them down, take notes, answer them, try to attempt, right? But if you don't want to attempt, you kind of want to save it for later after we do the summary. Feel free to skip all of these and go straight to the summary, and then come back and kind of do them if that's how you prefer studying. I did it this way, this first, um, for kind of more smoother format setup type thing for the computer, for the video, for recording. So, but yeah, because again, OChem 2 is so different from OChem 1 that most of you guys will just need practice and practice and practice, seeing those questions, seeing those, you know, reactions, things like that. So, okay, so pause, take a couple minutes, and let's see what answers you guys have for me. So, one, you guys should have gotten C, right? So in electron impact mass spec, so mass spec is what we're calling it for the most part in the class, in the lab, things like that. What is being detected? Molecular mass, molecular formula, mass to charge ratio of neutral species. So what's the difference between ionic and neutral species? So we know for mass spec, right, What's our axes? Our axes are abundance, and what's on this one? Mass to charge ratio, right? So um, that's what we have for C and D, mass to charge ratio. And ionic species, neutral species, we know that mass spec deals with ionic species because that's how they get broken up. That's how we get the plus ones, right? That's how we get those little itty bitty um, readings, right? Things like that or something, right? So ionic definitely. So it always has to be ionic because um, that's what mass, that's what the fragments, and that's what the lines, right? The readings indicate because of the ions that form from those fragmentations, right? And it does tell us the mass. Um, it can help us with the formula, but that's an aftermath of the mass to charge ratio of ionic species, right? So, okay, for two, you guys should have gotten C. And why C? You observe a compound exhibits mass spec with at 160 and then at 162 both equal intensity. So 160, 162. We know equal intensity means bromine, right? Bromine. But what about 1 to 3 ratio, right? It's going to be chlorine. So, and this is, well, we'll talk about it later at the review, but yeah, 1 to 1 ratio, bromine, right? Okay, so now we go to 3, the functional group region of infrared spectrum. And you kind of notice how there's not a lot of, we didn't say a lot with mass spec because mass spec is literally just that, right? Mass spec. We will focus more on infrared, things like that. And then um, next chapter, you'll get more graph and all that jazz, charts, things like that. And then everything's going to be combined at the end. So that's what the use of these are. So 3, you should have gotten B, right? And we know that, our, right? We care about 1500 and above, right? We don't care about this side so much, right? So that's the fingerprint, right? And then the functional group region. So just concept, nothing too crazy. So definitely be familiar with that. And this actually will come back later because you know, they can try and trick you by trying to make you find all these little ones over here, but it's irrelevant, right? Irrelevant. So compared to CH bond, a CH bond will vibrate where in the infrared spectrum. So for this one, 4, you should have gone C, lower wave numbers, and why is that? So CH versus CD. So what is the D? So D is deuterium, right? So D, we're running out of room, but CH, CD is deuterium. Deuterium, right? Deuterium is pretty much H2, right? So it's like a, it's a heavier hydrogen, and we know how CHs are very all the way up here in the infrared, right? Because they're light, they vibrate, they're pretty strong bonds, sp3s, right? So we find them over here in the 2000s. But CD, this is a heavier hydrogen, so it's going to be lower wave number compared to the CH, right? So okay, 5, you should have gotten C. What is the infrared absorption for the stretching motion of internal alkynes? And we know internal alkynes. C does not involve a dipole moment because symmetrical alkynes that are nonpolar, right? Symmetrical, nonpolar is IR inactive. Inactive. So it doesn't really matter what they do because, um, yeah, symmetrical and nonpolar, and that's what alkynes are, right? Okay, now in six, which indicated exhibits the stretching absorbance at the largest wave number? So you should have gone for this one, A. And why is that A? Again, right? Stronger the bond, higher, um, higher the wave number. Stronger the bond, higher the wave number, right? So nothing too crazy. Um, you guys have seen this before in lecture. I mean, right? Okay, so let's go to the next one. Okay, so again, pause, do them, screenshot whatever you want to do. Check your notes, um, attempt to do them, or feel free to move on and, do these later. But we'll be answering these. So seven, again, so it's kind of same question as six, but this time the lowest wave number. And what did you guys get? You guys should have gotten C, right? So this question always comes up every semester. I teach this or I SI this. What's the difference between 3 and 4? Right. So even though 4 is also an sp3, um, sp3 bonded, right? It's just single bonds adjacent to it. That double bond right next to it still affects the IR, right? So think about that. Obviously, think about as kind of like the dipole moments, right? Polarity, where it's getting pushed from, where it's getting taken away from, right? So same concept. 8, you guys should have gone. This one's a good one too. You guys should have gone A, right? So A. So for this one, you just needed to get the mass for 1, 2, and 3, and which one's 72. So 1 and 3 are actually both 72. So you guys should have got that down to 1 or 3. But there's an IR at 1715, and that's a carbonyl. So which of these two have the carbonyl? One, right? So that's that. For 9, you guys should have gone D. You were given a bottle of organic liquid, cyclohexanol. Which statements are true about these two compounds? D, hexene will show an absorption at 1650, right? Again, because of that double bond, and cyclohexane will not because it doesn't have a double bond. And both of them will show CH absorptions because they both have CH bonds, right? So it makes sense to me. What about why is it not A? So the two compounds can be differentiated with their mass spec, but they won't be because they're the same mass and they'll fragment the same way, right? Okay, so last one on this page, 10. An alkyne CH absorbs a higher wave number than an alkene CH. What does this tell you about the strength of those two bonds? Obviously, um, 10 would be B because alkynes are stronger, right? And we saw that number 7 and number 6. Well, actually, number 6 because that's when the highest wave number was asked. So, right, nothing too crazy. And I guess I forgot to mention that these reviews will have 20 questions each, and usually each test is 3 chapters around there, right? So each chapter you'll have 60 questions to practice on. So good deal, right? Good deal. So tell your friends to get these videos, and it's always good in video form because they're always there. You can always access them. You can always screenshot a fresh set of new pages, right, or whatever. And yeah, hopefully this helps. Okay, so let me erase this and let's move on to the next one. So 11 through 14. Pause again. Take your time, and when you're ready, come back and see what you guys got. Okay, so 11, you guys should have gotten C. And why is that? Molecular iron peak in mass spec 69 shows prominent peak at 2250. So C, both is 70, which is true, right? Um, oh, sorry, I was reading the wrong thing. The molecular mass is not 70 because it told us it's 69, obviously. So you can even cross out A, D, and E, right? So you should be down to B and C. And it's saying the prominence peak at 2250. So which one of those groups are in 2250? And it turns out 2200 is where cyano is at, the cyano group. So, and we just said earlier that um, carbonyls are in the 1600, 1700, right? So CO 1600-ish, right? And as time goes on, this is going to be one of your best allies. Um, Once you see that strong peak, right, 1600 strong peak, that's a carbonyl. You're good. You can go on from there. Those are one of the most common ones, most prominent ones. So you'll definitely see that time and time again. Hopefully. Okay. 12, you guys should have gotten. This one's a good question every semester as well. 12D. And you, if anything else, you guys should have gotten it down to 1 and 4. And now, because they're the same mass, and it's saying signals at 3000 to 2850, but none at 3000 to 300, 3300. So the peak at the 2800 range is sp3, sp3 ch bonds, while the ones at the 3000, 3300 is sp2 ch bonds, right? So we don't want any sp2 ch bonds. But you see here, this one has the sp2ch bond, right? So that can be it. So this is all ch3s over here, right? H, H, H. So ch3, ch3, sp3, 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 right? So that one's a good one because don't forget about the invisible H's, right? Okay, so 13. Again, this one is one of the most common ones. Um, D, because of that carbonyl, right? So carbonyl, um, 17, um, things like that. So nothing too crazy. And actually, this one, let's change it to 17. Okay, so 17 CO. Yeah. Okay, 14. Oh, there's another one here. 14, in typical mass spec, a smaller signal is observed at mass 1 AMU higher than molecular iron peak. Why? Impurities, machine error, um, small percentage of compound will have a carbon that is isotope of 13 instead of 12, C, because of fragmentation. So it's not impurities. It's not machine error. And fragmentation, it's not going to fragment one atom at a time. Like, what fragment has one? Hydrogen, but it's not going to fragment that way. And this is where the ions come in. 13C and 12C are isotopes, obviously, right? And when you put a molecule through the mass spec, it'll either stick to the 13C or the 12C, and that's where the ions come into play. So that's why you always have the um, M+1, right? This is the mass, and this is the isotope, the +1. So that's kind of where that comes from. Okay, let me erase this, and let's go to the next page. And yeah, see, this is another reason why this is the format we're using, because I won't be able to recreate this by hand. So, and it's better for you guys. You can screenshot this real quick before you guys see the answers, things like that. So, it works out. Again, pause the video, take a couple minutes, and let's see if you get the same answer. Okay, so you guys are back. 15, you should have gone D, ketone. And again, why? We know ketones are R, R, O, right? So again, this carbonyl, right? We have it there, the strong peak, 16, 17, in the 17s, right? In the 17s, and then R groups, the other peak. Well, for sure, alcohols won't have the carbonyl. The amine won't have the carbonyl, right? And so we should be down with aldehyde, ketone, and carboxylic acid. But why can we take out the carboxylic acid? It doesn't have the big alcohol, right? OH, there's no alcohol curve. So we should be down to aldehyde and ketone, and we do the ketone because of the um, CH bond. So again, kind of the same deal with the other one. This is an aldehyde, right? And this has an sp2 CH bond compared to over here sp3 CH bond. So, and that's where um, that peak is on 15. Um, yeah, about 2800, somewhere around there is a sp3. 2800, right? And this is like the 3300 we said. Okay, so 16. This one's a good one. Um, you guys should have gone C, carboxylic acid, right? And we just talked about it. OH is the big one over here with um, the 3000 range, 3000, and then again we see that carbonyl, right? So if you have an OH and a carbonyl, most likely carboxylic acid, right? So it's not just going to be an alcohol. It's not just going to be an aldehyde. It's together. Okay, alcohol and actually let me redraw it. So something like that, right? So this is the OH and this is the CO, right? So see, you would have been stuck with this if I didn't have the review up. So okay, let me erase this and let's go to the next page. So 17, 18, 19, 20. Oh, this is the last one. So take a second, pause it, screenshot, work it out, get your notes, do whatever you want, and come back. So 17, you should have gone C. And you notice here they're telling us what CNMR is, and we're actually going to be talking about that in the next chapter, the next video, because that's on the next chapter. So CNMR is a technique which the total number of signals represents the number of unique carbon atoms in a molecule. Propose a structure that is consistent with the following data. IR includes one at 1603 and one 1495. CNMR 7 signals, so 7 unique, right? And 1 acidic proton. So let's start with acidic proton because that's where students mostly get hung up about this question. So which one of these have acidic proton? So you should have it down between 2 and 3. Why 2 and 3? Because of the carboxylic acid, right? Acidic proton 2 or 3. So that's out of the way, right? Now we have to deal with the let's go with the IR signals. The IR, again, we don't care about 1500 or less, so we just focus at 1603, right? So 1600, and you'll see this a lot as well, is the aromatic. Aromatic. So this is one of the common ones as well. So aromatic. So which one between 2 and 3 is aromatic? Both of them, none of them, 3, right? You see how 3 is a benzene, right? It has a double bonds, but 2 is just an alkene, a cycloalkene, because it's not fully, it doesn't have those other double bonds inside it, right? It's not resonating. So it's just that. So this is aromatic. And even if we get hung up about that, we can count the environments, right? We can count the CNMR, the unique carbons. So we set it over here. Okay, so how do we count the unique carbons? We count, so make sure it's not symmetrical, but it is symmetrical, right? So this is 1, 2, 3, 4, 5, 6, 7, right? These two over here are the same as this is 3 as well, and then this is 4. They're the same over here because it's symmetrical, right? So that's how you count that. So that's how we get C. So now for 18, you guys should have gone D, and this is what I was talking about. Why the functional group in the fingerprint region is such a big difference, because like they give us like more stuff from the fingerprint region than they did functional group region. So we can cross out 1499 and below, right? We don't care about those. We don't have to look for those. So this is the one we're talking about, right? This is the one that was right. Then here. So it says the 3000 range is the sp2ch, right? Which is what we have. Actually sp3 because of this over here. And then the 2900 is the sp2ch bonds. And then the 2200 is the nitrile. The nitrile, right? And then 1600 is the aromatic, right? And then that's it. That's all we have, right? That's all we need. So that's how we came up with the answer D. 19. Which of the following information is primarily obtained from an IR spec? This one's a good one. Or what have we been talking about? What are all of these? Functional groups, right? So obviously this one's a B. B. So IR, um, functional groups, mass spec, mass, charge, right? 20. You guys should have gone for this one. Why we should have found pi bonds is inactive, and this is kind of the question we got back in number 5, right? A, that alk, and this is a good representation of it. What I was trying to say. Look how symmetrical it is, right? Symmetrical, no dipole moment, no dipole, symmetrical. Um, so inactive. so it makes it inactive, right? So kind of that's the gist of it. That's the whole chapter. And now let me erase this. And here is the answer key, right? So for those of you guys want to do it on your own first and then come back for the explanations if you guys have questions. Um, so now let's, again, as promised, let's do the summary. So obviously we just talked about um, mass spec and infrared. So that's what we'll focus on. Mass spec. And these new videos for OChem 2 won't have the index or the little summary sheets as in OChem 1 because honestly the titles kind of say it all, right? The titles for each chapter is literally what we're going over, so there's not even a big deal. And you kind of notice that too. Even in OChem 1, towards the end, the titles are kind of just like, yeah, that's what we're talking about. So, you know, so first things first, mass spec gives us molecular weight and molecular formula. So that's what we can find from mass spec. So here forms radio cation. So that's the mass, right? Plus, and this is the going to be called our molecular parent ion. And that's what we're looking for, pretty much, right? And that's the biggest, or that's the yeah, that's the largest number you'll have, which is your rate, right? So how does this all come about? Well, this is how it's kind of gonna go down. So this is your mass, your molecule, right? And then your electron over here, and this is kind of what happens inside the mass spec. And then this is what you get, the molecular ion. And then all you're reading, right? All you're reading are the radicals and the cations. And this is actually the important ones. Cations. Those are the ones you're seeing the lines of, the little fragmentation lines, things like that. So yeah, nothing too crazy, right? And that's how you get n+1 as well. All those little fragments. So now we have our terms, base peak. So base peak is not the largest number, it's the tallest peak. Always the tallest. Tallest peak, right? And then you have your n+1 is going to be the isotope of your main one, of your main molecule, right? Because m is our main molecular weight, and then n+1 is the isotope off of that. So that makes sense. So again, so let's say we had this, right? So this is what it's going to look like. You have our m, n+1, right? And then base peak, right? So that's kind of what you're looking for. And again, relative abundance over here, and mass to charge ratio of ions. So that's what you're looking for, right? Nothing too crazy. So let's get to a new page because there's a little bit more for mass spec. Mass spec. So there's nitrogen rule, the nitrogen rule, and this one's a good one to kind of just know because most well most of the time your mass is gonna be an even number. So if it's an odd number, you know there's definitely a nitrogen in there somewhere, right? So n equals odd number, it has nitrogen. So odd number, so nitrogens, right? Odd number of nitrogens, odd number as well. And then M goes number, even number of nitrogens. So yeah. So for this one, for the even number, it's hard to tell if there's a nitrogen unless you're given a formula. So the most important takeaway from this is the odd number. So if you have an odd M, um, there's definitely nitrogen. If it's an even M, you may or may not have a nitrogen, right? Okay, and now we get to M plus 2. So this one's interesting because this most students forget this. M plus 1 is the normal one, the cation, the isotope, right? Whatever. So now M plus 2 is our bromine and chlorine. So bromine over here, our 1-to-1 ratio, right? 1-to-1 ratio, and then our chlorine, um, 3-to-1 ratio. So 3-to-1 ratio. So, let me, bromine, chlorine, right? So what's important about the M plus 2 is that, let's say we have this at 100, the other peak will be at 102. This one we have here at 100 as well. The other peak will be at 102. So that's what you look for. You don't look at the plus 1, you look at the peaks 2 away from each other, right? So that's how you know. That's how you know. And also M plus 2 is important as well because sometimes you'll get asked, um, this peak is even peaks. One of the peaks is at 100. Where's the other peak located? 101, 102, 103, 104, 105, 102, right? So this peak is has a ratio of 3-to-1. One of the peaks is at 102. Where's the other peak? 96, 97, 98, 99, 100. 100, right? So kind of like that. That's kind of how you'll use that. So now mass spec, we know the lines are all fragments, right? So what is the deal with the fragmentation? So fragmentation, we know, is alpha cleavage. So um, right on the dot, right? Right on the dot. So we'll end up with a radical, and then a cerium ion, and then we can have also a dehydration, and we'll get a radical as well, and then of course dehydration water, right? So those are kind of the types of fragmentation we're looking at. This one is important because you can't just fragment at any place you want, right? You can't just fragment. Oh, check this out. So this is kind of a guide, like a guide for you to kind of say, take a step back. You can't fragment everywhere, so let's look for an alpha cleavage. Let's look for, can I dehydrate something maybe, things like that. So yeah, that's it for that. Mass spec, nothing too crazy. If anything, um, yeah, very simple, quick summary. Um, you know, don't just screenshot it, don't just write it verbatim. Um, Rewrite it in your own words, or color it up, spice it up. So, or if anything, clean it up because that was kind of like there was too much white. I guess it was too bland. Make it interesting. Okay, now let's go to IR spec. So for IR spec, we know functional groups, right? Functional groups are main um, main target functional groups, and we obviously use infrared, and we know that between UV and IR causes the bending and rotating, right, and stretching. IR breaks it and goes to another electronic excited state, right? Excited state. So it goes up a level. So that's kind of what to look for. This is high and this is low energy, right? And this is important too, UV and IR. You'll get questions from that as well. So now we have obviously here the V is the wave number, right? Wave number is absorbed and shows the bond here. The higher the bond, the higher the amplitude, right? Higher or yeah, stronger the bond, stronger the amplitude. So we know from physics, amplitude, the height of the waves, right? So higher amplitude, right? I don't have room for the E, sorry. So let me try. Higher amplitude. So wave number is the things getting absorbed, and the stronger the bond, the higher the amplitude. And you kind of see that with the carbonyls, right? That's a strong bond, CO, and then we know hydrogen bonds are all the way on the left, right? And it's really strong as well. So I think that's kind of what you look for. So the remaining, this is kind of how it works inside the spec. Remaining light is detected, right? And those are your functional groups. Functional groups. So um, these, so the way IR works is kind of bouncing off of each other. So me example, like there's light coming towards me. Obviously, it's bouncing off, and you're seeing my image, the colors, things like that. So that's kind of what IR is. But for like smaller molecules, right? Okay, so let's go to a new page. IR spec. So now we kind of did this earlier, right? Percent transmittance, and then what's over here? Wave number, right? Wave number. So we know 1500 is our cutoff, right? This is our fingerprint region, and then our functional group region, which we care about. We don't care about this, right? We care about this. So now what's the trend? So we always kind of you you're gonna get in lab or in class, wherever, you're gonna get your charts, like where everything falls. But in and we kind of talked about this in the with the review. In general, stronger, lighter, and that's why CH1s. That's why sp3 CH1s, even though they're not strong, they're super light, right? Stronger, lighter bonds equals higher wave number, and then vice versa. Vice versa. Weaker, heavier bonds are lower wave numbers, right? And that's because of Hooke's law. And this is like all physics, but it makes sense because we have the wave number over here equals k, and this is kind of the formula they use. F M. So this is the bond, right? And this is the mass, obviously. So yeah, stronger the bond, stronger the mass, higher the frequency. So stronger equals high. What's the frequency? Frequency. Frequency, right? And just I guess side note over here, we mentioned it a couple of times. Symmetrical, um, non-polar bonds are IR inactive, right? So, and again, feel free to redraw this, things like that, and you'll definitely get your sheet. But depending on your professor, some of them want you to memorize it. Some of them will give you that sheet as you take the test, things like that. So, just depends. Ask your professor. Ask your SI. So, with that being said, that's all I have for you guys. Nothing too crazy, fairly short, right? Pretty quick, and you know, no problem, no problem. Good reviews, and again, you're gonna have 20 each chapter, each video. So hopefully it helps, and hopefully you guys utilize them. And with that being said, thank you guys for watching, and I'll see you next time.